Welcome to our Chapter 6 lessons, dear students, looking at the neutralization of acid rain. In our new chapter, we'll look at topics such as, is acid rain considered normal? Is it worse in some parts of the country than compared to others? And is there a way to neutralize acid rain? And in our introductory picture, we look at corals in our oceans made of calcium carbonate. We understand that calcium is an elemental Ca, and then the polyatomic ion called carbonate, CO3. We've learned last chapter that calcium is an ion that carries a +2. Carbonate is an ion, polyatomic ion, that carries a -2, so it's an electrically balanced ionic compound. Calcium carbonate is what corals are composed of, and amongst other things, like a major component even of chalk and of limestone. When they dissolve in acidic conditions, we're soon going to learn that acids, a class of chemical family, are those types of elemental reactions that contain a hydrogen ion. And what we end up seeing is that calcium ion gets decomposed or gets just changed out to have H2CO3. I have to come down here. So I'll have H2CO3. And the calcium ion then is let go in its aqueous form. We would be calling it an electrolyte in our last chapter, Ca2 positive, an aqueous ion. This H2CO3 is what we commonly refer to as carbonic acid. And this carbonic acid, H2CO3, I'm going to actually write its name for us, carbonic acid. Acids we're going to learn in our new chapter are those substances that start with an H. H2CO3 came from carbonate, the polyatomic ion. Putting an H in front of it turns it into an acid. Hydrogen we know is a +1, carbonate's a -2, and we end up with a crisscross to equalize those charges, H2CO3. But this is a pretty unstable acid, and what happens is, as soon as that acid forms, it's going to decompose and give us carbon dioxide and molecular water. Carbon dioxide we know to be a gas, and liquid water, which again, if this is in the ocean, contributes to just the liquid form of water. So we could see that calcium carbonate in the presence of an acid destroys the corals by breaking the calcium carbonate down literally into carbon dioxide and water. CO2 will bubble out of the water, leaving a little remainder there. All kinds of bells and whistles going off, I apologize. What does the word acid mean to you? Well, here we see a Cleveland Press headline from a while ago, obviously, that acid rain is killing Ohio's neighbors. Well, if being from Michigan, this is quite concerning because Michigan is an Ohio neighbor. But you can also see that because of the large amount of industry on the shores of Lake Erie, and that industry is releasing nitrous oxides, we'll just NOx for now, where X represents a subscript on the nitrous oxides. Even sulfur oxides are going to emit these gases into the air, and when they react with the water, either contained as moisture or coming down as precipitation as rain, they are going to form acids. And the acids are going to contribute to a change in the normal pH of rainwater and start to increase its acidity. And we'll talk about in our new chapter the pH, the measurement of how acidic or how basic a solution is. I also see just some common everyday lemons in this picture. Lemons contain an acid known as citric acid. Citric acid is a common household ingredient in many of our citrus fruits. Vinegar is an acid. It's called acetic acid. It has a formula from that polyatomic ion we call acetate. The common name of HC2H3O2 is called vinegar, acetic acid. And again, there are some acids that are quite helpful, and then quite harmful to our environment. We'll talk a little bit more at length about the pH scale, where 7 indicates a neutral solution. Numbers that are smaller than 7 on the pH scale are said to be acidic, and the numbers that are greater than 7 on the pH scale are said to be basic. We'll soon learn that acids and bases are opposites of one another. Let's begin with a brief definition of what an acid is. An acid is defined as any substance that releases a hydrogen ion when dissolved in water. An aqueous solution means dissolved in water. And the more hydrogen ion that's released in the water, the more acidic a solution becomes. Now remember, hydrogen on our periodic table has a mass number of 1 and atomic number of 1. If you find hydrogen on our periodic table, mass number over atomic number, the information we can glean from that, knowing, again, just review for us, that the atomic number tells us the identity of the atom. Hydrogen atomic number is 1. By definition, that's going to be one single proton, isn't it? And the mass number, by definition, is the sum of the protons and the neutrons. And we've been practicing that skill all semester long. So if I think about what this little box tells me, 1 minus 1 tells me hydrogen has 0 neutrons. Total parts in the nucleus are 1, and all of those 1 parts are a proton. So if I were to consider just an atom of hydrogen, it has a single proton and 1 electron residing out here, 1 single electron. This is an atom, which is neutral, but we know that hydrogen is highly unstable with its 1 valence electron. When it loses its electron, I'm going to make that note as saying just loss of 1 electron, it forms what we call an ion. And notice if I just simply erase this whole outer shell here, what we end up with is that we have that electron being released. All that's left is a single proton. And so in this slide, what it really says is when hydrogen ion forms, a hydrogen ion, when it loses its electron, it's just a free-floating proton in the water. The loss of this electron simply leaves a single proton. So you'll often hear hydrogen ion and the word proton interchanged. They are indeed the same thing. Here's an example of what we're referring to. Any substance that releases hydrogen ions in water is called an acid. HCl, hydrogen chloride, in the gaseous form, when dissolved in water, is an electrolyte. An electrolyte, we learned, is a substance that, when dissolved in water, breaks apart into the ions it's composed of. And ions are charged. We learned that a cation is a positively charged atom, and an anion is a negatively charged ion. When they're together, hooked together by electrostatic attraction, HCl is the compound, but when they're placed in water, they break apart and dissociate. They form the ions they were built up. So remember, this hydrogen ion is completely surrounded by water molecules, and the chloride ions are completely surrounded by water molecules. And just to remind ourselves about that process we learned last chapter, remember that water is polar, and it has a very strong attraction to oppositely charged areas. Well, I just drew that wrong. If the oxygen is actually the negative region, we're going to see the positive area attracted right here, H plus, to the negative region on the oxygen. We start to see this completely surrounded. So this hydrogen ion is surrounded by water molecules, a very strong hydrogen bond. And the chloride does the same thing in water, doesn't it? Chloride is negative, so you'll start to see the water molecules completely surround the chlorides based on opposite charges. And we'll see that completely surround and drawing them in to dissociate the ions. So the attraction for the ions to the water is much stronger than they had to each other, and that's why they fall apart when they dissolve. So all of that to just share why a hydrogen ion is actually the same thing as a proton. It just simply dissociates, lets go of its electron, and surrounds itself with water. And when we consider how strong that proton is attracted to water, we can see what I just drew actually a moment ago. Our water molecule and that original hydrogen ion that was released from the acid, this guy right here, H+, when it actually is in the water, that free-floating proton attaches to the water. I mean, it has no chance of just free-floating around by itself. It's always attached on to a hydrogen and the water. And what we call this species is a hydronium ion. Hear that word? Hydronium, H3O plus 1. It's really called a protonated water molecule. It's water with an extra proton. Protonated water molecule. And I'll abbreviate molecule, MLC. So oftentimes you see this written as H+, the protonated water, but it really is H3O+ when I see it solvated by the water molecule. Any species that dissociates, lets go of, same words, lets go of a hydrogen ion, starts with an H and it lets go of a hydrogen ion, will be called an acid. Acids are hydrogen ion producers. That hydrogen ion attaches onto the water, and it's really written as hydronium, H3O+. So we said acids are a class in chemical family. Acid properties would contain very sour tasting, such as lemons and vinegar. Acid turns litmus paper red. Now, litmus is an acid-base indicator, and you'll probably use that in the lab, acid-base indicators. My little saying, and it's a little helpful, acid is red. If you say it right, see how it rhymes? So if I had a piece of blue litmus paper and dipped it into some vinegar, or blue litmus paper and dipped it into some lemon juice or orange juice or lime juice, it's going to turn the paper red. Red is acid. Acids have pH values below 7, so the smaller the number on the pH scale, the more acidic the solution is. So below 7, acids. Acids react with carbonates to form carbon dioxide gas. So again, I just modeled that on the opening slide, and we'll see that as a repeating theme over and over. Carbonate is a polyatomic ion, CO3 minus 2. It would take 2 positive protons, 2 hydrogen ions, to neutralize that minus 2 charge from carbonate. And the species that formed we called carbonic acid, H2CO3. My pen won't go over that far. H2CO3. There, we got it. And then we said as soon as this species forms, it's very unstable. And what you'll start to see is this H2CO3 decomposes, and out comes carbon dioxide, leaving behind liquid water. So acids, those compounds that start with H, react with carbonates. Carbonates is our polyatomic ion, major component of the coral, those lovely structures in the water. They form carbonic acid and release then the CO2 plus water. Acids are the opposite of bases, so acids are said to neutralize bases, and we'll look at this chemical equation in detail in just a few more slides. And acids often dissolve some metals. So acids, let's just say, for sake of picking one, HCl, hydrochloric acid, can react with an element, any metal. Oh, should we pick, how about zinc metal? Zn, the elemental form of zinc is Zn. We called this type of reaction a single displacement. So what happens is this element zinc is more active on our activity series, and it steals away the partner, forming the new compound zinc chloride and generating hydrogen gas, H2, the molecular form of hydrogen. And of course we would need to balance that equation. So here is where we have our overall general formula. An acid, any substance that has an H in the beginning, reacts with a metal. And when it does so, it produces a new ionic compound. It will be a salt. A salt is our species where we have a metal hooked to nonmetal, where we crisscross charges. We practiced this last chapter. Ionic compounds are called salts. And what's released then is the hydrogen gas, Hydrogen, hydrogen gas. And that would be the observation we would make is that this gas would come out and you'd literally start to see it start to bubble. And it's a very exothermic reaction. So all of these properties are about acids. Acids are the opposite of bases, and they neutralize one another. And we'll refocus on that in a moment. So we're looking at examples of those things that start with H. Hydroiodic acid. Iodine. Hear that root word iodine? Hydroiodic acid. Nitric acid comes from the polyatomic nitrate, nitric acid. And this is called sulfuric acid. We commonly hear it called battery acid. Sulfuric acid. It comes from that polyatomic ion called sulfate. H turns to ic and we get sulfuric acid. Well, what would it look like if hydroiodic acid dissolved in water? We'd have HI, hydroiodic acid, going into some water, forming the hydronium or protonated water molecule and iodide, I-1, the aqueous ion called iodide. HI dissociates, it separates, and when H separates from the iodide, we know that the water molecule is going to snatch it up very quickly. That free-floating proton in the water doesn't stand a chance of remaining unattached. This hydrogen ion that came from the acid protonates the water. So H3O plus is our acid ion, leaving behind the negative anion called iodide. Nitric acid does the same thing. Nitric acid is a compound that starts with H, and so we have HNO3. When it's placed into water, dissociates. Now remember, even though there's many elements here, it's still a positive hydrogen and the negative polyatomic called nitrate. So this is one ion called nitrate. We called it a polyatomic ion. The proton is released and protonates the water molecule. So here's our acid species called hydronium, and what's left behind as the negative anion is nitrate, NO3, -1. Now keep in mind, you might also see this written. It just really varies by the text or by your instructor. Some instructors will place the water over the arrow and just simply want you to put hydrogen ion and the nitrate ion. Knowing that any time a true chemist sees an H+ hydrogen ion or the proton, it's automatically assumed we know that it's attached to the water as hydronium, that these two are indeed equivalent to one another. And the last one had a diprotic acid, H2SO4. When the diprotic acid forms, we end up with a species releasing two hydrogen ions. And so this would look like, let me get my pen, H2SO4. And we can show it where the two hydrogens are released to make 2 units of the acid ion, H+, leaving me the polyatomic ion called sulfate, which carries a -2. This 2 here came from the fact that sulfate was a -2. Notice that this is just one polyatomic ion called sulfate. This is one polyatomic ion called nitrate. And if we indeed showed this with the water molecule, we could then see that it would take 2 water molecules to satisfy both protons to create 2 hydroniums. And that last polyatomic ion, SO4, 2 negative. Both of these protons require a water molecule to become a hydronium. So just kind of checking through, acids are those substances that start with H. The H attaches onto the water molecule, forming the acid ion known as hydronium. And this is what we measure when we measure something known as pH. With a piece of litmus paper, or perhaps with a more sophisticated device, a pH meter that gives us a digital readout. But pH is a measure of the concentration. Remember, those brackets stand for molarity units. pH is a measure of how acidic or how basic a solution is. And we'll soon learn that it's a logarithmic function, which is based on the power of 10. And we'll calculate it by saying it's the negative log of the concentration of the hydrogen ion. And that concentration we know to be big M, molarity units. Moles per liter of our hydrogen ion. So you can see the more and more protons we have, remember these two are equivalent, hydrogen ions and hydronium. The more concentrated we have a hydrogen ion solution, the lower its pH becomes, the more acidic it will become. And again, these are coming. I'm just seeding the lesson. What does it mean to be strong versus weak in terms of acids or bases or electrolytes in general? So again, we're referring back to our last chapter on the lesson of electrolytes. We understand that a strong electrolyte, I spelled that wrong, electrolyte. That's not even close. That's what happens when you try to talk and write at the same time. Electrolyte. This is the lesson we're referring to as a strong electrolyte 100% dissociates in water to ionize in water, and we saw the light bulb glow brightly. A non-electrolyte is 100% molecular, no ions at all, and the light bulb glowed none. But the weak electrolyte partially ionizes and gives a little bit of a light bulb turned on. So let's kind of compare a weak acid to a strong acid. Now the strong acid we're looking at is called HCl, hydrochloric acid. When hydrochloric acid dissolves in water, 100% of it pushes to the right to form our hydronium ion and our chloride ion. And literally over the arrow, I'm going to show that 100% of this reaction pushes right. So by the time I'm done, there's no reactants left. We're 100% on the right side of the arrow. Hydronium is at H3O plus and chloride is negative. And this is what we refer to as a strong electrolyte. And remember that this concentration is what we measure how acidic or basic a solution is with our unit known as pH. If we compare acetic acid, which is vinegar, it's a weak acid. So a weak acid only partially ionizes in water. It's not very good at letting go of the ions. And I'm going to exaggerate that with this kind of arrow. It says about 1% of the molecular form of acetic acid exists as ions at any one particular moment. And so, I gotta write this down here. This C2H3O2 negative, acetate, a polyatomic ion, carries a -1. So remember, H is a +1. Acetate, even though there's a lot of letters here, it's still just one polyatomic ion. It carries a -1 charge, so they are indeed electrically balanced. Same up here, hydrogen is a +1, chloride is a -1, so it's electrically balanced, HCl. That means at any one particular moment, 99% of this molecule is in the molecular form. So this is what we refer to as a weak electrolyte. And if I just write the word weak, that just simply means a little bit of it exists as ions at any one particular moment, but not very much. So a weak electrolyte may turn on the light bulb a little bit of electricity being conducted, but certainly we could consider that if this is what we're measuring with a pH scale, acetic acid does not change the pH of pure water as significantly as a strong acid such as HCl. If pure water has a pH of 7, where it is considered to be neutral, if I add a strong acid such as HCl, I'm really affecting the pH by putting in a lot of the acid ion. If I add a weak acid, such as vinegar, to neutral water, I'm not affecting the pH as much because I really haven't put in a significant amount of hydronium ion. Only about 1% of the original molecule put in an acid ion. So, what about that flip side of acids? The chemical opposites of acids are called bases. Acids and bases are opposites of one another. A base, sometimes you'll hear the word alkaline, such as an alkaline battery, if that sounds familiar. Just writing that in there so you hear both words. An alkaline compound or a basic compound produces hydroxide ions in water solutions. Characteristics of bases, they taste bitter. Think about, did your mom ever make you take a bite of soap for saying a naughty word? A bitter taste. They're very slippery in terms of feeling like again, soap or a cleansing agent. They turn red litmus paper blue. So blue and base both start with B's, and that helps me remember blue is base. And remember our little rhyme from before? We said red is acid and blue is base. So just kind of that litmus test, which is just a little piece of paper in the lab where you'll just dip it in the solution, see what color it turns to know if it's acidic or basic. So a compound that releases hydroxide ions are OH -1. Again, this is a polyatomic ion, isn't it? Two atoms bound together carrying a charge. A good example is sodium hydroxide, and this is commonly sold as a compound called lye. NaOH as a solid form, when dissolved into water, forms aqueous ions. It releases sodium, Na+1, in an aqueous form, and hydroxide, the OH -1, as the hydroxide, polyatomic ion. Now think about why water is neutral. I'm just kind of seeding why is that a neutral compound. Do you see, just kind of in its structure, how we could have H positive and OH negative equal parts acid and base. The acid is the proton and the base is the hydroxide OH minus. When I have a molecule that contains equal part acid and base in the structure, it's going to be neutral. Acids and bases neutralize each other, and so its pH would be exactly 7.0. Not acidic nor basic. Acids have a pH below 7, bases have a pH above 7, and if it's exactly at 7, the solution is said to be neutral. Acids start with H, bases end with OH. Here's an example. Calcium hydroxide, when dissolved in water, releases its ions. Notice that we have a calcium 2 positive and 2 equivalents of the base ion hydroxide. That 2 came from our subscript here. Calcium, we learned last chapter, is in group 2A, therefore we know it's a positive 2 charge. Hydroxide, our polyatomic ion, it carries a -1, so when they crisscross to write our electrically neutral compound, calcium hydroxide, Ca, parentheses, OH, taken twice. We need 2 groups of the hydroxide to electrically balance the calcium plus 2. This is considered to be a strong electrolyte because it 100% dissociates when placed in water. 100% of it lets go and separates into the ions surrounded by water. What about ammonia, NH3? Ammonia is a base through and through. It turns litmus paper blue. It feels slippery. It is bitter to the taste. It's a great cleansing agent. It does everything a base is supposed to do, but it has no H group at the end. Well, we can explain that with a little bit of chemistry. When ammonia, NH3, actually dissolves in water, we form a compound, ammonium, a polyatomic positive, hydroxide, a polyatomic negative. See how the water included in the ammonia compound shows the hydroxide necessary to define bases end with OH. And then I can see ammonium hydroxide letting go to dissociate the hydroxide. And there's our definition of the base, ending with OH. So ammonia is kind of a rule breaker. It's a base through and through. It's actually considered to be a weak electrolyte because really only about 1% of it is ever going to form ions at any one time. So a better indication of this would be that exaggerated arrow we drew before to represent weak electrolytes. 99% of ammonia at any one point is in the molecular form. Now remember, in terms of the definition of bases, when we're measuring the pH, what we're measuring is the concentration of the hydroxide ion to know if it's acidic, basic, or neutral. The power of the hydrogen ion compared to hydroxide will soon be discussed. We'll talk about how to calculate pH of compounds who start with H, which are acids, see how that's a direct match, or compounds that end with OH, which are bases. We can still work to find its pH, and I'll show you how to do that momentarily. Acids start with H, bases end with OH. And again, we can consider, just as acids, that we have strong bases and weak bases. Strong bases completely dissociate, weak bases do not. Strong acids completely dissociate, weak acids do not. Same idea, it just has to do with the equilibrium arrow. If we just consider what weak means, it's a little bit going to dissociate, but not very well, versus the 100% arrow pushing all those ions to the right. How do you recognize an acid from a base beginning with their formulas? The very definition of acids say, I will see a hydrogen written in the first position. The hydrogen ion is always written as the positive ion. Hydrogen chloride would be named hydrochloric acid. Hydrogen carbonate is called carbonic acid. Hydrogen sulfate is called sulfuric acid. Hydrogen nitrate is called nitric acid. See how they all start with H. Bases end with the polyatomic ion hydroxide. Hydroxide defines the base. Sodium is the first name of sodium hydroxide. Dissociating to let go of hydroxide makes it a base. Magnesium hydroxide and barium hydroxide are all examples of those compounds whose last position, the anion, the negative ion, is the hydroxide polyatomic. Except ammonia. Ammonia is a base through and through, but doesn't contain the OH hydroxide in its formula. I strongly suggest just to memorize when you see the structure for ammonia, NH3, we've drawn it several times throughout our lessons. Here's our Lewis dot structure just to remind us that ammonia has nitrogen as a central atom. 2 lone pairs makes it a polar molecule. And if I consider what happens here when I react it with a water molecule, which is also a polar molecule, these pair of electrons grab that proton from the water, cleaving the bond. So you end up producing ammonium NH4 plus 1, an extra proton, cleaved right off of that water molecule, snatched it right away. So here is the ammonium, which I'll put in a bracket so you can see it's an ion now carrying a +1 charge. And what's left? Well, it's the hydroxide, -1. Hydroxide, OH, used to be part of the water. The nitrogen's lone pair of electrons snatch the hydrogen from the water molecule, leaving us the polyatomic of OH, -1. And this makes this a base. Anything that releases hydroxide ion is defined as the base. When an acid reacts with a base, they neutralize one another. It's called a neutralization reaction. The pattern of chemistry says when an acid reacts with a base, H goes to OH, Na goes to Cl. When an acid reacts with a base, they neutralize one another by forming a salt. The salt in this example is NaCl, and the neutral water molecule results. Remember that the water was formed by taking the acid component hydrogen and hooking it to the base component of hydroxide. HOH, the water molecule, equal part acid as compared to base. Sodium ion and the chloride ion form the salt, NaCl, and the H from the acid and the OH from the base make the water. So in a neutralization reaction, hydrogen ions from an acid combine with the hydroxide ions from the base, forming a neutral water molecule. Acid plus base makes salt and water. Sodium chloride, an electrically neutral compound. The positives balance the negatives. We call ionic compounds salts. Here's some practicing from your homework section on sapling. Let's write the neutralization reactions for the following examples. And I'll work down here. The first one says sulfuric acid, H2SO4, and I'm going to react that with the base called potassium hydroxide. I strongly recommend just considering the charges the ions carry. Hydrogen, which is a +1, and sulfate is that polyatomic ion, and I know it carries a -2. This 2 is telling me that when I uncrisscross. Hydrogen, which is +1, sulfate is a -2, so H2SO4 is our equivalent compound. Potassium lives in the first column, so it's a +1. Here's the base ion called hydroxide, and it is a -1. And the reason I like to do that is when we go outer inners, H goes to OH, K goes to SO4, these two positions, the two positive ions, are going to exchange partners. Alrighty? So H goes to OH. Hydrogen is a +1. Hydroxide is a -1. We commonly write this as a water molecule, but I'm just showing you HOH is electrically balanced. And so just remember our pattern. We have an acid plus a base is going to produce water and a salt. So we have the next SALT is salt. We have to write the formula of our salt. So here's potassium. Its formula is still K+1, the aqueous ion of potassium, but its last name is going to be sulfate, the polyatomic ion who carries the -2. So when we crisscross charges to get an electrically balanced compound, that 2 has to be placed after the potassium to have 2 units of your +1. So H2SO4 plus KOH yields water, either as HOH, but you recognize that as H2O, and the salt of potassium sulfate. We also need to balance, and when we balance, we have to have equal number of each ion on both sides. So as soon as I noticed I had a diprotic acid, 2 hydrogens, I knew it would take 2 base units to balance the 2 acid units, giving me 2 water molecules. 2 protons, 2 hydrogen ions, require 2 hydroxide or base ions to electrically balance and neutralize. There's our first example. When HI and barium hydroxide, so here we have hydroiodic acid, HI, hydroiodic acid, H1, I -1. And the base is barium hydroxide, BaOH taken twice. Here we have barium as a +2, hydroxide as a -1. When an acid reacts with a base, they neutralize to form a water and a salt. And the salt has to also be electrically neutral based on charge. So keep in mind we have hydrogen +1, hydroxide -1. When an H combines to an OH, they make a water molecule, HOH. Equal part acid as base. Now remember, water truly is written as H2O, but sometimes it's just helpful to see that the hydrogen came from the acid molecule and the hydroxide came from the base molecule to create an electrically balanced compound. And what about the salt? Barium would be its first name. Barium carries a +2 charge. It's in group 2A, so Ba2 positive. And it's going to be attached to the negative iodide, I -1. And when I crisscross, I get BaI2, barium iodide. We need to balance. It would take 2 acid ions to neutralize both of those base ions, giving us 2 water molecules. A 2 to 1 to 2 to 1 balances that equation. Boy, we have a triprotic acid in H3PO4. This is called phosphoric acid, H3PO4. It is going to react with a base called sodium hydroxide, NaOH. Let's predict if we have 3 acid ions being neutralized there by the phosphate polyatomic ion, PO4 is polyatomic phosphate, and we have it reacting with sodium hydroxide. How many of these base ions do you predict will need to neutralize all 3 of those protons? I'm with you. I'm going to predict that, we don't know yet, but it's going to be a 3. H3PO4, 3 protons. So when an H goes to an OH, H is a +1, hydroxide is a -1. We commonly just write this as H2O, that's our water. But HOH helps me see that H came from the acid and the OH came from the base. And I can easily see that the OH, all 3 of them, were necessary to balance the 3 protons on that triprotic acid. So we'll end up making 3 waters. And the salt would be sodium, who's a +1. The last name is the polyatomic ion called phosphate, PO4 -3. So we get Na3PO4. Our salt is called sodium phosphate. When an acid reacts with a base, we produce a salt and water. And there's one more on here. We have HCl with barium hydroxide, and that's your last one for this homework slide, so we might as well finish it. We have HCl with barium hydroxide, BaOH, taken twice. And remember, acids start with H, they're +1s. Chloride is a -1. Barium is a +2, hydroxide -1. So when H goes to OH, we make a water molecule, electrically balanced with 1 proton and 1 base ion. And the salt that is produced has the first name of barium, who carries a +2, and the last name of chloride, who carries the -1. And so when we crisscross, we get BaCl2. And when we balance, we know right off the bat how to predict that. Since there's 2 base ions, we're going to need 2 acid ions to neutralize, resulting in 2 water molecules. You're doing a great job. We're going to stop our first lesson here, give you time to process what we've learned so far. When you're ready to come back, we're going to take a next step and talk about those reactions we were just practicing and truly how to break them down into what's called a net ionic equation. You've done great work so far. Let's pause and come back when ready.